Hello. In this lecture, I am going to discuss about the calculation of pH for a weak acid. Okay, for weak acid as well as for weak base. Okay, so we are going to discuss pH of a weak acid or weak base. Okay. We know that weak acid or weak base, okay, weak acid or weak base will undergoes only partial ionization. Okay, weak acid or a weak base will undergo only partial ionization, and we also know that the acid the molecule which undergo ionization, okay, only those molecules will provide H plus ions. Okay, so only ionized molecules or ionized species, right, produce H plus ions. Okay, in the case of weak acid, it produces OH minus ions in the case of weak base. So keep this in mind. Only the ionized species will provide. What is meant by that? Ionized means molecule which undergo ionization. Okay, see, weak acid and weak base undergoes partial ionization. Only the molecule which undergoing ionization, okay, produce H plus ions, right? Yeah. And since it undergoes only partial ionization, so suppose I will take a weak monobasic acid. Okay, let us assume that HA is a weak monobasic acid. Okay, if I put this acid in water, okay, what will happen? This molecule or the molecules of weak acid will undergo ionization. Only partial ionization takes place. Therefore, what is meant by partial ionization? Suppose if I put 1000 molecules in water, okay, out of 1000 molecules, only 5 or 10 molecules will ionize, right? So it will undergo only partial ionization, right? Only few molecules will ionize. So I will get H plus ion in aqueous medium and A minus ion in aqueous medium. So the unionized molecule remains as HA. Only the ionized molecule provides H plus. Okay, so that's the meaning, right? Only the molecule which ionized produce H plus ions. So to find the concentration of H plus ion, if you want the concentration of H plus ion, right, what we have to do? We must find how many molecules actually undergone the ionization, or number of molecules ionized, that we have to find out. Okay, instead of number of molecules ionized, we can also find fraction of molecules ionized, right? Fraction of molecules ionized is represented as alpha, also called degree of ionization or degree of dissociation. Degree of dissociation. Okay, so only the molecules which are undergoing dissociation produce H plus ion. Therefore, to find the concentration of H plus ion, we need to find the value of alpha. What is alpha? Alpha is called degree of dissociation. Okay, now how to find degree of dissociation? What is degree of dissociation? First of all, alpha is nothing but number of moles of the molecule dissociated, a number of moles of species. I'll use the general term species. Number of moles of species dissociated. Species means molecules in this case. Okay. So number of moles of molecules dissociated divided by number of moles of molecules taken, moles of species taken initially. Okay, this is what we called as alpha. Once you calculate alpha, or once you find the value of alpha, then you can find the concentration of H plus ion available in a solution containing weak acid. Okay, very specifically weak monobasic acid. Yeah. Now to calculate the concentration of H plus ion, right, in a solution, we proceed like this. Okay, what we have to do, let me first take some amount of water in a beaker. Okay, so we have water. Now some amount of water. Now I'll put 1 mole of a weak monobasic acid HA. So HA is the weak monobasic acid. I'm adding 1 mole of the acid in water, so that we'll get a solution. Now let us assume C is the concentration of weak acid. Okay, C is the concentration of weak acid, assuming, right, C is the concentration of weak acid, assuming weak acids are not ionized. What is meant by that? We have added 1 mole of HA. If all the HA molecule remains as such, if they do not undergo any dissociation, then the concentration of the acid is C. But we know very well, weak acid molecules, these molecules undergo partial ionization. Therefore, the actual concentration of HA in solution cannot be C. It should be less than C. Okay, so now what we have to do to understand this, I'll take this HA, weak acid molecule, in aqueous medium. It will undergo partial ionization, produce H plus ions in aqueous medium and A minus ions in aqueous medium. Okay, now initial number of moles, right? We have taken initial moles. We have taken 1 mole of acid. Let us assume that initially acid is not dissociated, so we have 1 mole, no H plus and no A minus. Now what I'm going to do, at equilibrium, right, as a dissociation takes place and the reaction will attain equilibrium, right? At equilibrium, let us assume from 1 mole alpha mole is dissociated. Okay, therefore number of moles at equilibrium, is, see, from 1 mole alpha mole is dissociated, therefore the number of mole at equilibrium is HA. For HA is 1 minus alpha, and for H plus is alpha, for A minus is alpha, because one molecule will give 1 H plus and 1 A minus. So alpha mole, if alpha mole dissociate, we'll get alpha mole of H plus and alpha mole of A minus. Okay, now suppose if all the 1 mole of HA are not dissociated, if they are not dissociated, then the concentration is C. Okay, if 1 mole remains as such, then the concentration is C. But what happened? Because of the partial ionization, only 1 minus alpha mole is remaining at equilibrium. For 1 mole, concentration is C. For 1 minus alpha mole, right, concentration is 1 minus alpha into C. Therefore, concentration at equilibrium is equal to, for HA, the concentration at equilibrium is 1 minus alpha into C. For H plus, concentration at equilibrium is alpha into C. For A minus, concentration at equilibrium is again alpha into C. So to find the H plus ion concentration, okay, in a solution containing weak monobasic acid, okay, you need this value alpha into C, right? So let me write the next page. So H plus ion concentration, right, called and also called equilibrium concentration, right? H plus ion concentration at equilibrium is equal to alpha into C. So if you calculate the value of alpha, C value is known, right? Because we only prepare the solution, so we know the value of C. We need to find the value of alpha. If we know alpha, If you multiply alpha into C, you will get the equilibrium concentration of H plus. Once you know the concentration of H plus, you can calculate pH directly. Okay, then you can also write, since there is an equilibrium, see this reaction, reversible reaction attains equilibrium, you can write equilibrium constant. So equilibrium constant for this reaction can be written as, let me write here, equilibrium constant K. I'll put subscript A here because it is a weak acid. So equilibrium constant for the weak acid, also called dissociation constant of the weak acid, also called as ionization constant of the weak acid. So this is nothing but ionization constant of a weak acid. Okay, Ka can be written as, okay, since it is an equilibrium constant, you can write Ka as equilibrium concentration of H plus ion, equilibrium concentration of H plus ion into equilibrium concentration of A minus ion whole divided by equilibrium concentration of HA. Okay, so we need equilibrium concentrations. Equilibrium concentrations are available here, so I am going to substitute those values here. So Ka is equal to alpha into C into alpha into C over equilibrium concentration of HA is 1 minus alpha into C. Okay, if I cancel this C and this C, I'll get alpha square C by 1 minus alpha. So Ka is equal to alpha square C by 1 minus alpha. This is the ionization constant of a weak acid. Okay, and remember, Ka is a constant for a given weak acid at a given temperature. Ka is a constant. Ka is a constant for a given weak acid. For a given weak acid and at a given temperature. At a given temperature. So at a particular temperature for a particular weak acid, Ka is a constant. For example, for acetic acid, the value of Ka is 1.8 into 10 power minus 5. Right? Don't worry about the unit. Just remember the value 1.8 into 10 power minus 5. Similarly, if I take formic acid, for formic acid, the value of Ka is 1.9 into 10 to the power minus 4. Okay? And these are all values, these are all constant values at 25 degrees Celsius. Okay, at 25 degrees Celsius, this is the ionization constant of acetic acid and this is the ionization constant of formic acid. It's a constant. Right? Now if you observe this carefully, Ka is related with the alpha and H plus ion concentration is related with the alpha. Therefore, we can relate H plus ion concentration with the Ka directly. How? Yes. For this, what I am going to do, let us suppose assume that okay, if alpha is very much less than 1, okay, that is, we can say that if alpha is less than 0.05, right, 0.0 less than 0.05 means 5%. If degree of dissociation, you can even put equal to, if degree of dissociation is equal to 0.05 or less than 0.05, okay, or I can say the other way, if degree of dissociation is 5% or less than 5%, then we can say that this 1 minus alpha, since alpha is very very small, you can neglect this alpha, right? So 1 minus alpha is equal to 1. Therefore, if I substitute this in this expression for Ka, so in the Ka in the denominator, okay, under the assumption that alpha is very less than 0.05 or less than 0.05, this denominator become 1. If denominator quantity becomes 1, then I can write Ka is equal to alpha square into C. This approximation is valid only if alpha is less than or equal to 0.05. Okay, therefore from this you can write, bring the C here and take square root. So I can write alpha is equal to square root of Ka by C. Right? You can determine degree of dissociation using this formula. Right? Using this formula, calculate alpha value. If alpha value is less than 0.05, yes, that equation is this assumption is valid. Okay, yeah. Now what I'm going to do, so H plus ion concentration at equilibrium, okay, for a solution containing monobasic weak acid, H plus ion concentration at equilibrium is given as alpha into C, and now we know the value of alpha, right, under the assumption that alpha is very, very small. So if I put this alpha here, I'll get square root of Ka by C into C. If I bring the C inside square root, it will become C square. So C square, if you cancel, you will get the value as root of Ka into C. Right? So keep this in mind. You can calculate H plus ion concentration, equilibrium concentration for a weak monobasic acid using these two roots. Okay, you multiply alpha into C, you will get H plus alpha into C, or you take square root of Ka into C, that also will give you H plus. Right? So depending upon the problem, see whether alpha is given or Ka is given. If alpha is given, alpha into C will give you H plus ion concentration. If Ka is given, root of Ka into C will give you H plus ion concentration. Okay, so using that you can calculate H plus. Once you know H plus, you can calculate pH. Yes, how to calculate pH? You know the formula. Let me write to the next page. The formula is this: pH equal to, see, this is the actual formula. Okay, without any approximation. But this formula, okay, is an approximate one. What is the approximation? Alpha should be less than or equal to 0.05. Then only you can use this one. This is without approximation. Okay, this is the perfect formula. This is perfect formula, whereas this one is an approximate one. Okay, now what I'm going to do is that, so what is pH? pH is minus common logarithm of concentration of H plus ion. Okay, now I'll put minus common logarithm H plus ion concentration, right, under the assumption that alpha is very small. We can write it is nothing but Ka into C whole power half. Okay, so here what is the assumption? The assumption is alpha should be less than or equal to 0.05. It's very small. Now bring this off in front, therefore I can write 1 by 2 into this can be written as minus log base 10 Ka minus log base 10 C. Okay, or we can write this as 1 by 2 into minus log Ka is nothing but pKa minus log C base 10. We can use this formula to calculate pH of a weak monobasic acid. Okay, but if you want to use this formula, you should this condition should be valid. Alpha should be small. Then you can use this formula. If alpha is not small, if alpha is greater than this, greater than 5%, then you can use this formula to calculate pH equal to negative logarithm of, in the place of H plus I'll put alpha into C. You require alpha. Okay, so this can be written as minus log base 10. Yeah, I think this is enough. Yeah, you can calculate pH using this formula. Okay, this is without approximation, and this formula is with approximation. This is with approximation. So this formula is an approximate formula. What is the approximation? Alpha should be less than or equal to 0.05. Then only you can use this. Okay, yeah. So using these formulas, you can calculate pH of a weak monobasic acid. Okay, now let me do one or two problems so that you can easily understand this concept. question. Calculate, okay, let me write like this, 0.2 molar aqueous solution of a weak acid, 0.2 molar aqueous solution of a weak acid has pH equal to 3. Okay, calculate pKa of the acid. Calculate pKa of the acid and given, what is given here is alpha is very less compared to 0.05. Right, alpha is very small. Okay, now so the assumption is given, or this condition is given. Under this condition, you know very well, we have direct relation for pH. So pH equal to half into pKa minus log base 10 C. You can use this formula directly under the condition that alpha is less than 0.05. Okay, now pH is given, pH is equal to 3 here, 1 by 2 into, we need to find pKa minus log base 10, concentration is given 0.2 molarity. Okay, I'll bring this 2 here, 3 into 2 is 6, 6 is equal to pKa minus log base 10, 0.2 can be written as 2 into 10 power minus 1, or 6 equal to pKa minus of log 2 10 power minus 1 can be written as 1 minus log 2, 1 minus log 2. So 6 pKa plus 1, log 2 value is 0.3, so 6 equal to pKa, 1 plus 0.3 is 0.7, or pKa equal to 6 minus 0.7, it is 5.3. So you can calculate pKa for an acid, for a weak acid, for the given data that 0.2 molar solution has pH 3. Okay, some weak acid, monobasic acid, monobasic weak acid has pH equal to 3. Calculate the pKa. For this question, we have to proceed like this. But remember, if you want to use this formula, this condition should be satisfied. Okay, this condition should be given. Right, now let me do one more problem just to make you comfortable in this calculation of pK of weak acid. Right, okay, say 0.001 molar acetic acid, aqueous acetic acid, okay, is given. We need to find the pH of the solution. Okay, 0.01 molar aqueous acetic acid is given. For this, we need to find the pH, and what is given here is given is Ka. Ka for acetic acid is 1.8 into 10 power minus sorry, 1.8 into 10 power minus 5. Okay, now we need to calculate the pH of the solution, but we cannot use the formula directly. K is available, but to use the formula, you must know whether alpha is small or not. So how to check it? Yes, alpha is equal to square root of Ka by C. Use this formula. Okay, alpha is equal to root of Ka value is given 1.8 into 10 to the power minus 5, and concentration is given 0.001, which is nothing but 10 power minus 3. Okay, square root of 1.8, the value of these are values we should remember actually. Sorry, let me give you the value. be around 1.4, I think so. Anyway, yeah, let me give the value. The value for 1.8, square root of 1.8 is 1.34. Okay, students, try to remember this value, because often for pH calculation they'll give acetic acid. So for acetic acid, Ka value is 1.8. Therefore, square root of 1.8, okay, is a very important data. So you need not do square root and all. You can try to remember this value. Square root of 1.8 is 1.34. Okay. Then if I bring this 10 power minus 3 to the numerator, I'll get 10 power minus 2. Square root of 10 power minus 2 is 10 power minus 1. 10 power minus 1, okay, into this is 0.134. 0.134 is greater than 0.05. It is greater. Therefore, we cannot use the formula as such. Okay, we cannot use the formula as such. So what we have to do? We have to calculate alpha. So you know very well, Ka is equal to alpha square C by 1 minus alpha. Right? We have to find out the value of alpha exactly. Okay, what to do? Just put this value here, 1.8 into 10 power minus 5. Alpha square, you keep it as such. Concentration is 10 power minus 3. 0.001 is nothing but 10 power minus 3 divided by 1 minus alpha. I'll bring this 10 power minus 3 to the left hand side. So I'll get divided by 10 power minus 3. If it goes to the numerator, it will become 10 power plus 3. So if you do simplification, you'll get 10 power minus 2 into alpha square over 1 minus alpha. Okay. Then now I'll multiply this by 1 minus alpha. So I'll get alpha square minus 1.8 into 10 power minus 2 alpha, then plus 1.8 into 10 power minus 2 equal to 0. We will get a quadratic equation, right? If you solve this quadratic equation, you will get the value of alpha. You can find the value of alpha. Once you know the value of alpha, you can calculate the value of H plus ion concentration, right? H plus ion concentration is nothing but alpha into C. So find the value of alpha, substitute that value here, and calculate H plus. Once you know the value of H plus, you can calculate pH of the solution. Okay, so before proceeding any problem, okay, it is very, very important to find the value of alpha. If alpha is greater than 0.05, then you have to use this actual formula and find the value of alpha using that. You will get a quadratic equation. You need to solve it. Okay, I'll just leave this as an exercise to you. You try to find out the value of alpha and calculate the value of H plus ion concentration and calculate the pH. Okay, good. Now, so this is how you must proceed for weak gases, right? Now, let me do one more problem, just for making you understand the concept. 0.02 molar aqueous formic acid is 10% ionized. Calculate the pH of the solution. Calculate the pH. This is the question. Concentration is given, and it is given that 10% ionized. Okay, so what is the concentration given? The given concentration is 0.02 molarity. Alpha value is 10%. 10% means 10 by 100, which is nothing but 0.1. Okay, now alpha is available and concentration is available, so we can use this formula to calculate H plus. That is, H plus ion concentration is alpha into C, right? Alpha value is 0.1 and concentration is 0.02, so you will get 2 into 10 power minus 3 molarity. Okay, if you multiply this, I will get 2 into 10 power minus 3 molarity. This is the concentration of H plus ion. Once you know the concentration, you can calculate pH. How? pH equal to negative logarithm of base 10 concentration of H plus ion, which is nothing but 2 into 10 power minus 3. This you can write directly as 3 minus log 2. Log 2 is 0.3, so 3 minus 0.3 is 2.7. So pH of the solution is 2.7. Okay, so in this way you can calculate pH of any weak monobasic acid. Right? In a similar manner we have to proceed for weak bases. Okay, for weak bases what we have to do is for weak base, pH of a weak base, what we have to do is we have to proceed in a similar manner. Instead of Ka we'll get Kb here, that's all. So concentration of OH minus ion, since we are using weak base, concentration of OH minus ion can be calculated sorry, for a weak monoacidic base. For a monoacidic weak base, okay, for a monoacidic weak base, concentration of OH minus ion can be calculated using the formula alpha into C. This is actually exact formula. Exact. If you know alpha, you can calculate OH minus concentration exactly. Or you can use this formula square root of Kb into C, as we discussed for weak acid. Okay, I am using the same formula here, but instead of Ka I put Kb. What is Kb? Kb is the ionization constant of weak base. Okay, but this formula is an approximate one. Okay, why it is approximate? Because we are assuming that alpha is less than 0.05. Under this assumption you are using this. Okay, so this will give you exact. So you can calculate the concentration of OH minus using this formula or this formula. This will give you the exact value, but this one will give you approximate value. This approximation is valid if alpha is less than 0.05. Okay, once you know the value of OH minus concentration, then you can calculate POH using the formula minus common logarithm concentration of OH minus. Okay, after getting the value of POH, you can calculate pH, because we know very well pH plus POH equal to 14 at 25 degrees Celsius. I have told you already, if temperature is not mentioned, you have to assume the temperature is 25 degree. Okay, so POH value, you can calculate POH value using this. Once you know POH, yes, you can calculate pH. Right? Yeah, this is the method we have to proceed for weak base. Okay, yeah, I stop here. In the next class, we'll discuss how to calculate pH for a dibasic weak acid, right, and a mixture of a strong acid and weak acid. Those things we'll discuss in the next class. Okay, I stop here. Thank you.